Okay, we're ready. Great. So, before we start today, let me just make a couple of announcements. I should probably give you guys a midterm sometime, maybe sooner than later. I'll announce this over Canvas as well later today. But the midterm will be on Friday, the 28th of October, in class. And I'll design it to take the entire class period. Okay, so we'll have at least one more problem set. I might have a back-to-back week for. Yeah. Is that? Oh, 29th, right?
Yeah.
Sorry.
Because the
Yeah, we have an E&M one on the 28th.
I was gonna say, I was like,
Sorry.
I thought I had something on Sunday the 31st, and now I know that messed something up.
Yeah, my mistake. Okay, right. So the 29th of October will be the midterm. It'll happen in class. I'll design it to take slightly less than the whole class period. We'll have at least one more problem set. I might try to cram 2 problem sets in there because we're going to cover a lot of material in the next 3 weeks. Okay. Secondly, let me just say there are a couple of typos on problem set number 2. Okay. The first one, a bunch of people pointed out to me, right, which is on 2B. Just choose A. Primitive cubed root of unity. Right? The goal of that problem is not to say that any primitive cubed root of unity times z, whatever it was defined as, gives you a triangle of the same area. And I also just wanted to say, problem 2b points at some idea of a conjecture that I haven't taken the time to verify, but after you've worked on this for a while, here's the conjecture. First of all, similarity of triangles is an equivalence relation, right? Any two, that is to say, all the triangles that are similar fit into the same class of. They're all similar to each other, and they're not similar to anything that is not similar to everything in that class. But I would like to say, what I would like it if somebody showed, or maybe I'll take the time to do this over the weekend, is that every similarity class of triangles can be represented by a choice of primitive cubed root of unity times the appropriate complex number z. Okay, so in other words, you can produce a triangle with an arbitrary admissible triple of angles by just multiplying the appropriate complex number z by a primitive cubed root of unity. That's where this problem came from. So think about that. It's kind of fun. It's an elementary geometry problem, right? That doesn't mean easy. That just means you can say it without using the machinery of modern mathematics, right? So you don't have to think about it now, but if you're bored, if this lecture bores you, think about that. Secondly, only one person pointed this out to me, and I recognized it. I should have said something earlier, but I had some kind of morbid curiosity on number 1, part B. We should have m strictly greater than 2, right? I bet, even though nobody said anything, they probably realize that, right? There are only one primitive square root of unity, and it's -1. So clearly, the thing I asked you to show is false when m equals 2 in problem number 1, part B. Okay, so those are the only typos I know of.
There was one, I think.
Oh, I bet I know what you're going to say. When I expressed the product in part number 1C, I used
The R.
the limit of the index instead of the index. Yeah, that's true. So this is, I'm sorry. This is what it's like. This is what it's like to have me as a professor. I make mistakes all the time. Okay, so number 1C. What I actually meant was, if I recall correctly, I used this notation, z minus omega j, right? Not omega r. Yeah, thank you.
That's what it should be.
This is what it should be. I wrote r here. Yeah.
Just like out of curiosity, if someone were to submit like tomorrow or today, that 1B isn't true, is true, would you have given them points?
Yeah.
Full points?
This is my fault. So yeah, that's fine.
I was gonna say m equals like 0.
Well, what does it mean to take the 0th power of something?
Oh yeah.
Or rather, you can't take a 0th root because 1 over 0 is not defined.
Exactly.
Yeah.
I was gonna disprove the whole thing.
Yeah. So let's see if anybody wrote that. But now that I've told you the correction, maybe I'll be less lenient.
So I should have skipped class today.
Well, yeah. Not that I ever advocated for that, but yeah, maybe you should have skipped class today. Okay. So one more announcement. I was just hanging out in Harvard Square, and I went to this bookstore called The Raven, which is a used bookstore that is kind of a repository for when professors retire and move, or maybe unfortunately pass away. Their estates are often liquidated, and a lot of their textbooks go to this used bookstore in Harvard Square. And so I periodically go in there just to see what there is to see. I got this book by Felix Klein. It's actually a translation of the original German from 1895 called Famous Problems in Elementary Geometry. I picked this book up just at random. And there's actually a chapter in here about cyclotomy, the historical origins of why we care about cyclotomic polynomials. So quite fortuitously, I picked this book up. So I copied the chapter. This is just of historical interest. This doesn't help you on the problem set in the least, but it's kind of interesting to read nonetheless. Don't tell anyone I copied you copyright material.
It's the whole book, or?
This is just the chapter 3. Yeah.
This is the paper.
Right. So yeah, look over that at your leisure. Sorry I copied it all stupid. You know, it's upside down in some parts, right? But yeah, I don't know. Interesting reading if you're in the mood. Right. One final announcement. Don't forget, the problem says due at midnight tonight, or 11:59 p.m. Okay. So it's not totally useless that I'm telling you this now.
Do you know what time 9 p.m. is also open to?
I'm sorry. Say that again.
Like what time? Like the latest we can drop off the problem set visit?
Oh,
Like when it closes?
that's a good question. I know there's a card reader on the door, so I think
Okay.
you can open the door anytime. But I don't know that. Yeah. To be honest, it's if it turns out you can't turn in a physical copy and you don't want to submit a digital copy, I'm not going to balk too hard at that. That's okay, but let me me know if that's impossible when you want to turn it in.
Yeah, it's more like, I was wondering if like it closed at like a dump time, like 8 p.m. or something.
Yeah, I really don't know the answer to that, I'm sorry to say, but, yeah. Let me know if you try to turn it in later than that. Maybe we can meet sometime over the weekend and I'll pick it up. Because I do want to have a fast turnout, nonetheless. Okay, so, right. PS number 2 to 11:59 p.m. If you can turn it in, if that's even possible.
And is the place to turn it in like outside 548?
Yeah, it's an envelope pinned to the door that you entered in when you came to visit for office hours. There's 2 doors to my office. One of them has 3 envelopes on it, the other one, none. You'll see it labeled clearly. 4555 assignments. Okay? Okay. Logisticals out of the way. So, we left off on Tuesday with the definition of analyticity. And this is so important that I think I'll just write it again. So it's really internalized by us all. Okay? So, recall. Actually, this is not enough space. Why don't I start on the fresh board? Recall. A complex function f is said to be analytic on an open set G. If f has derivative at every point of G. Okay? And the point that I really tried to stress as we were all leaving class on Tuesday is that analyticity is a condition that is defined in terms of an open set G. Okay, so it's a stronger condition than saying that a function is differentiable at a point. And we're saying, technically we're saying infinitely many more things, right? Because an open set, we didn't prove this, but an open set of C must contain either no points or infinitely many points. It's either the empty set or some other thing which doesn't contain its boundary. Okay? So, right, and then I pointed out this misleading convention of terminology where we say f is analytic at a point to mean that there's some open set containing that point in which f is analytic. Right? So I'm not going to write that down again, but that's equally important. Remember that. Okay. So, here's some additional definition, which will become quite important to us, especially when we start to talk about integration. Okay, so a point where f is not analytic but which is the limit of points where f is analytic is called a singularity of f, or a singular point. Okay, so this is kind of counterintuitive behavior, right? How could we have a point which is the limit of a point where f, the limit of a bunch of points where f is always analytic? That is to say, around each of these points we can find a neighborhood in which f has derivative. But at this point, this singular point, we are not analytic. We can't find a neighborhood. Yeah.
Could the function, like in the real numbers, if there was such a definition of like analyticity in the real numbers, could the function 1 over x at 0 be considered, or at 0 be considered a singular point?
Well, let's think about this for a second.
Because it would be like quote unquote analytic up to 0.
Yeah, right. So what's the interpretation of an open neighborhood? Or open set G is just an open interval. Yeah, right. So that's a fine example. Yeah, I have the function 1 over x in the real numbers. But the distinction here is that the definition of analyticity for real numbers, for real functions, carries less weight, has less implications in the sense of real numbers, right? And it does have an interpretation. It does have a meaningful interpretation in terms of functions of a real variable with a real output. And we'll see that in chapter 5. But yeah, topologically, that's a good example to think of, right? You can find an open interval in any point that is not 0 of f of x, f of x, which is equal to 1 over x, where you're differential everywhere in that neighborhood. But there's no neighborhood of 0 that in which you're differential. Okay? Good. So, in our context, so, e.g., what we know from the examples we discussed on Tuesday, a rational function is analytic for all points z for which the denominator is non-zero. Okay? So again, if you make a comparison with real functions, this is just like we were talking about, right? There's a singularity at 0 for the function 1 over x. But in contrast to real functions, what we'll see in chapter 3 is that we can use the singularities of a complex function to make a fast computational formula that's almost as nice as the fundamental theorem of calculus, that depends on where our function is 0 and where it has singularities. Okay? So there's somehow more information contained in the singularities of a complex function than of the singularities of a real function. Okay, so furthermore, let me just say f of z, some complex function, is called entire. If it is analytic on all of the complex numbers, right? That is to say, for every complex number, you can find an open neighborhood such that f is differentiable. Or another way of saying this is that f is differentiable everywhere. Right? That's the simple interpretation. That's what it means to be entire. Okay, so let me just say, like polynomials, for example. Okay. So our motivation in giving a definition of analyticity was to characterize these functions, these complex functions, which treat a complex number z as a whole number, as a number in its own right, i.e. not splitting up the components, real and imaginary. Okay, so, and our goal in defining analyticity was to give an effective condition for checking this for an arbitrary function, right? Something that we can look at, feed into a computer, and verify whether we're analytic or not. Or, that is to say, treat z like a quantity in its own right. So, this is one of the few times that we'll talk about a couple simple differential equations. We can further reduce this technical condition of analyticity, right? That is to say, given an arbitrary function, it might be quite laborious to check analyticity by the definition. Okay? But if we consider some properties of the first partial derivatives, we come up with a condition that is much easier to check. Okay? This will result in the all-powerful and prevalent Cauchy-Riemann equations. Okay? So, let's look back. Remember, we compared, when we proved that what was it? When we proved that the conjugate of z was not a analytic function, or not admissible was the term we were using at the time, we considered approaching the limit as delta z approaches 0 in two different ways, right? In a way parallel to the y-axis, and a way parallel to the x-axis. Let's revisit this example. Okay? So, let's suppose that f is differentiable principle, at z naught equal to x naught plus I y naught. And furthermore, that f of z is given by, as we've discussed, two real value functions of two variables, u of xy, plus I times v of xy. Okay, then we compute. Just from the definition, what we know is that this is equal to the limit as delta z goes to 0 of f of z naught plus delta z, minus f of z naught divided by delta z. Then compute this in two ways. I should say colon. Horizontally and vertically. Okay. So, horizontally, what we have is, remember we discussed delta z just becomes delta x, right? We have a fixed y, so our difference in z just becomes change in x. Okay? And written out explicitly, what we get is the limit as delta x approaches 0. Now I'm going to substitute in my decomposition into two real functions. Okay? So I get u of x naught plus delta x comma y naught, right? My delta y is 0 when I'm horizontal. Plus I times v of x naught plus delta x comma y naught minus u of x naught comma y naught. Sorry, I'll distribute the negative here. Minus v of x naught comma y naught, all divided by delta x. What does this remind you of? Something from calculus 3. Yeah, this is just the partial derivative. The partial derivative with respect to x, right, of both u and v added together, right? So that is to say, let's be really explicit here about how we manipulate limits. And oh, I forgot an I here. Sorry. That probably seemed confusing, right? So I'll combine my imaginary components and my real components, and because of the properties of limits that we know, we can split the sum across the limits, right? So that is to say, this is equal to the limit as delta x approaches 0 of u of x naught plus delta x comma y naught minus u of x naught comma y naught divided by delta x plus I times the limit as delta x approaches 0 of v of x naught plus delta x comma y naught minus v of x naught comma y naught divided by x naught. Okay, so as you just observed, Joseph, these are just the limits that define the partial derivatives of each of these functions, u and v. Right? So we get partial u, partial x, plus I times, well, really I should say this is evaluated at the point x naught comma y naught, plus I times particle v, partial x, at x naught y naught. Okay? So, I bet you can guess what I'm going to say next. Right? I told you we were going to compute this derivative in two ways. Now we'll compute it vertically. Okay? So in the vertical case, what do we get? Delta z, we're not changing x at all. X is a fixed value. So delta z is I delta y, right? It's just I times the difference in the y coordinates for our moving point that's getting closer to z naught. Okay? So similar computation shows, what do we get? That f prime of z naught is equal to the limit as delta y goes to 0 of u y naught, I'm sorry, x naught, x naught, comma, y naught plus delta y, minus u times, I'm sorry, u of x naught, comma, y naught, divided by I delta y, plus I times the limit of my imaginary component. The limit as delta y approaches 0 of v of x naught comma y naught plus delta y minus v of x naught y naught divided by I delta y. So what do we get here? We get, this is all equal to 1 over I, right? I can pull this constant 1 over I out of the limit of the partial derivative of u with respect to y So I pull my 1 over I out here, I get I divided by I is just 1. Right? Plus the partial derivative of v with respect to y. Or if I rationalize my denominator, what do I get? I multiply by the conjugate of I in the numerator and denominator here, so I get a negative I. Right? I get a negative 1 from the denominator and just an I in the numerator. Okay? I get a, sorry, I said that wrong. I get,
That's right. If I squared in the denominator, I on top.
yeah,
Yeah.
right, so I get a negative I in total. Good. Okay, so yeah, I get negative I times partial u partial y plus partial v partial y. Okay, so now I computed the same number, the derivative of f at z naught, in 2 different ways, and I got 2 different answers. Oh, again, I forgot to say that these derivatives are evaluated at x naught, y naught. Okay, so altogether, what this is telling me is that partial u, partial x at x naught, comma y naught, plus I times partial v, partial x at x naught, comma y naught is equal to partial v, partial y at x naught, comma y naught, minus I partial x partial y at x naught, y naught. Okay, so remember, we have equality. Oh yeah, what am I saying? Partial u. So remember, equality of complex numbers depends on equality of both components, right? So in other words, what I get is a pair of relationships between the partial derivatives of u and v. So what do I have here? In general, I get partial u, partial x is equal to the real part of the other way I computed this, partial v, partial y, and partial v, partial x is equal to negative partial u, partial y. Okay, so these are the Cauchy-Riemann equations. Okay, so in other words, analyticity of the complex function f boils down to this relationship between the component functions, the real part of f and the imaginary part of f, u and v. Okay, this is really something we can feed into a computer and have check in a lot more cases than we could handle by hand. We were just using definition, right? That is to say, checking that at each point where you have an open set where we're differentiable everywhere in that open set. Okay? So, let's just record what we just said. So, if f of z equal to u of x comma y plus I times b of x comma y is differentiable, at z naught equal to x naught plus I y naught, then the Cauchy-Riemann equations, which I'll usually write as just the CR equations, right, just for brevity. Then the Cauchy-Riemann equations hold at the point x naught comma y naught for u and v. Okay, so again, just to emphasize our distinction between differentiability and analyticity, I'll say this in another way. If f is analytic in the open set G, then the CR equations hold for all points of G. Right? Just really, this is a mistake everybody makes a lot when they first start considering the difference between differentiability and analyticity. So I'm going to say it as often as possible that they're distinct. Do you have a question?
This is not true in reverse.
We're going to talk about that. Okay. Yeah. Good question. We'll soon see what's required for it to be true in reverse. There's a slight additional condition. Okay. So, but before that, let's just do an example just to get comfortable here. So let's show that f of z given by x squared plus y plus I times y squared minus x is nowhere analytic. Okay, that is to say, for any complex number z, we're not differentiable. And so this is, again, pointing to the weirdness of the distinction between differentiability and analyticity. To show something is nowhere analytic, it suffices to show that it's nowhere differentiable. Right? Okay, so what should we do here? Well, let's determine where in the complex plane. I'm sorry, yeah.
So just a question about the theorem. So if a function is differentiable at one point, that doesn't imply that it's differentiable in open interval around.
Correct.
Does not.
That's right. Yeah, right. When we, remember, we define differentiability only at a single point, right? And then we can say something is differentiable on some set if it's differentiable at each point. So the difference is when we say something is analytic is that, oh, it's analytic here means that we necessarily can find a set around that point where the function is differentiable.
Because with real numbers, it would imply that it is.
Yeah, that's right. So again, there's a distinction here between real functions and complex numbers. Complex functions, sorry. Yeah, good observation. Right, and if you trace it back, this is because of the possibility of coming from any direction. You know, or not just any direction, but any path. Infinitely many paths to converge on a complex limit, not just directions. Right? There's nothing that says it has to be linear. You could like spiral in toward a point, for example. Okay, so yeah, that's good. Okay, so if we want to show that f of z is nowhere analytic, what we should do, is my suggestion, we should characterize the subset of the complex plane for which the Cauchy-Riemann equations hold for u and v. And then we know that those are the points where it's differentiable, right? Then we have to determine if we can find an open set around any of those points that has our function f be differentiable in that open set. Okay? So let's see what the Cauchy-Riemann equations tell us. I.e., let's take some partial derivatives. Okay? So first of all, u of xy is just equal to x squared plus y, and v of xy is equal to y squared minus x. Okay, so what's the partial derivative of u with respect to x?
2x.
It's just 2x. Good. Okay, what's the partial derivative of u with respect to y? It's just 1, right? I think somebody said 1. Good. Okay, how about the partial derivative of v with respect to x? Oh, sorry. Let me ask you first why, just so we can organize this nicely on the board to look at the Cauchy-Riemann equations. What's the partial derivative of v with respect to y? It's just 2y. Okay, and the partial derivative of v with respect to x is just negative 1. Okay? So, that is to say, 2x must equal 2y, and negative 1, right? Negative of, oh geez, I forgot my partial here. Negative 1 of the partial of u with respect to y is equal to the partial of v with respect to x. Is where the CR equations hold. Okay, so we have a tautology from the second Cauchy-Riemann equation, and we actually get a condition on x and y from the first Cauchy-Riemann equation. Okay, so this is to say the CR equations are only satisfied along the line that's the only way to make these two things equal. Yeah?
Applicable question. When we think of lines, we think of lines as infinitely thin, right?
Mm-hmm. Yeah, yeah, right, so you see where we're going here, right? The points, the complex number z equal to x plus iy have to satisfy this to satisfy the Cauchy-Riemann equations for this function that we wrote down f. Okay? So for any point z equal to, say, x plus ix, where f is differentiable, that is to say, here's my z-plane, right? Here's my line of complex numbers that satisfy the Cauchy-Riemann equations. If I take any point here and take an open set around it, and I draw it as an open disk, but you know, it could be more exotic, but it's fine to think of it as an open disk. None of the points off this line f is differentiable at, right? There's no way to form an open set around this point here, this fat point that I'm emphasizing. There's no way to form an open set around this in the z-plane such that all the points in the open set have f be differentiable at them all. It's only the points along the line where f is differentiable. Okay?
Is that, so like for this particular example, I know it's like pretty obvious that you can't make any open sets because it's just a line, but is that something we need to like actively prove?
I'm not going to ask you to prove that,
Okay.
but it is something worth proving.
So like any line that has a different slope, none of the points are going to fall on the line that you've already said, right?
Well,
Because I like to have an open set around it. A line with every slope has to have some point that goes like that goes to that point has to always have a point in the open set for it to be able to like, right? Because there has to be something around it at every point. So like every potential slope of a line around it that goes to that point has to have something else in the line that falls in there, and that's not true for any line that doesn't have the slope of one.
the way you're phrasing this, it makes me feel like there's maybe too much emphasis on lines in terms of what an open set is.
No, I just mean like for this particular example,
Yeah, yeah.
if you had to like prove it, could you say something like that?
So,
Couldn't you just say that there exists an epsilon greater than 0, where the local neighborhood of radius epsilon won't necessarily contain points outside of the line?
well, yeah, that's exactly what we're saying, right? That no matter how small you make this open ball, you'll contain points which are not in the line.
Right.
Is that equivalent to what you were saying?
Yeah, I guess my point is like, can we just, because like I know that it's true and it like graphically is fairly obvious, but can we just say that?
Yeah, yeah. I'm not going to require you to make any precise topological arguments outside of what we've discussed in terms of like the definition of open and closed and compact. Yeah, like I wouldn't require you to make an epsilon delta proof of this statement, right? Okay, good. I mean, in fact, if you ever find someone who makes you do that, I don't know, that would surprise me. I mean, because there are plenty of exercises that you will probably do when you study topology that will get you comfortable enough with the concept of an open set that this picture suffices to. And maybe that's disappointing.
No, it's great actually. I just wanted to make sure that I wouldn't have to do
Yeah,
that.
yeah. I mean, you know, like the the one thing you might try to say is like, okay, forget this open neighborhood that I drew. What if I just consider the points like on the line, an open interval on the line? Is that open in the plane? No, because any point in this interval, if I take an open ball, the point is that I'm in a plane, right? If I take an open ball around any point in here, then I'll still contain points that are not in the set that I specified.
And couldn't you also say that because it's its own boundary, it's closed?
Well, I note my use of open parentheses here.
Oh, yep.
So, not close.
Okay.
If I had drawn square brackets,
Yeah.
yeah, again, just a graphical convention, but a valid question. Okay, is this okay with everybody? Yeah. Good. Good. Okay. So now let's go back to the question that Luke asked. That is to say, in order to deduce differentiability of f from satisfaction of the CR equations, we must insist on slightly more. Here's the theorem. So, again, let's let f of z be equal to u of x comma y plus I times v of x comma y. Be defined in some open set G containing some point Z naught. So, if the first partial derivatives exist. Sorry, the first partial derivatives of what? Obviously, you know what I mean. The first partial derivatives of u and v exist and are continuous. At Z naught, and they satisfy the CR equations, again, at Z naught. Then we can say f is differentiable. At Z naught. Okay, so really all we're adding here is we insist that the first partials are continuous. Okay, that u and v are continuously differentiable. Okay, that is technically an extra assumption, but it's pretty mild, right? It takes some work to construct a function which is differentiable that has non-continuous derivative, right? Most of the things we encounter that are differentiable are continuously differentiable. So it is technically more, but like in practice, really you can go the other way, right? Okay, good.
Yeah. So just like a question about the differences between analyticity and differentiability.
Mhm.
If we find that f is differentiable at all z in G, then we find that f is analytic over G.
Yeah,
Okay.
yeah, that's right. That's exactly right. Right, so what you described is a constructive way of showing that some function is analytic in some open set G. If we're just told that the function f is analytic at a point, then we don't know what the open set is where it's differentiable. There's just some open set, right? So that's another subtlety of going back and forth between those two things, right? Yeah. So if you know exactly what open set you're trying to determine analyticity in, you just check differentiability at each point. But we'll soon be able to talk about functions being analytic in general, and not necessarily explicitly specifying what open sets around each point are differential.
Is that because like a function that is analytic has some special behavior that we can care about?
Yeah, right. It's because of, if you take it back to our discussion from Tuesday, it's because of this preserving the wholeness of the complex number Z. That's actually the root of the thing. I wish somebody had told me that when I took complex analysis in undergrad and graduate school, but that's really the point of analyticity, that you're trying to consider, you're studying functions which preserve the wholeness of the complex number Z. This whole business of admissible and inadmissible, which was admittedly like very imprecise, right? But this is just to give us an idea of what we're trying to capture with this condition of analyticity. Okay. Good. All right. Okay, so then the obligatory statement for analyticity related to this, right? If first partials are continuous and satisfy the CR equations, at all points of G open, then F is analytic in G. Okay. Sorry, just now when I was writing this C-R, I realized we talked about Riemann already, right? Anybody remember Cauchy?
Is it Cauchy series or Cauchy sequences?
Cauchy sequences? Hunter, do you want to add something to that?
I was gonna say Cauchy inequality.
The Cauchy-Schwarz inequality, good, yeah. Yet another important thing from analysis. Both of those things are really important in analysis, right? Cauchy, a pioneer of analysis, right? He determined a systematic way to add into the rational numbers all the additional numbers which we call real or irrationals, right? By defining this notion of Cauchy sequence, a sequence where the terms of the sequence get closer and closer together the farther out you go in the sequence, right? Very similar to the conditions that we put on limits of sequences of complex numbers, right? But a little more. Okay, so that's actually technically what a real number is. It's an equivalence class of Cauchy sequences. And maybe some of you have taken real analysis. It's great work what Cauchy did. Put analysis on solid foundation. Gave us a real language to talk about real numbers. Turns out he did a lot for complex numbers and differential equations as well. Okay? This is thematic of mathematical history. You know, if you go back several generations, every prominent mathematician, influential mathematician, didn't work in a single area of mathematics as we conceive of it these days, right? It was a time in which mathematics was more monolithic. It was just a single thing. The variegation that we see today is just from, in my opinion, product of people banging their heads against really hard problems of a certain type for a long time. Okay, so that's kind of why I photocopied these handouts for you, because you know, you'll see that synchrotonic polynomials actually arose out of trying to construct regular polygons inscribed in circles, right? So give that a read. I think it's really interesting. Anyway, enough history. Okay, let's return to an example that we had some question about when we were talking about admissible and inadmissible functions, right? Remember, we looked at the exponential function, e to the z, and we were like, well, our most useful expression of this is that it splits up the real and imaginary parts of z, right? E to the z is equal to e to the real part of z times e to the I times the imaginary part of z, right? Or you could express that in terms of sines and cosines. So let's ensure that the exponential function is a nice function, i.e. analytic everywhere. Okay? So let's let f of z equal e to the z, and my claim is that this is entire. That is to say, analytic in the whole complex plane. Okay, so how should we go about doing this? We should just verify that the Cauchy-Riemann equations hold for all points z, x plus I, y. And it'll be evident that the partials are, in fact, continuous. Okay? So, here's another way to write f of z. We have e to the x. Oh, sorry. I should say z is equal to f plus I, y. Okay. So f of z is e to the x times cosine y plus I times e to the x sine y. Okay? Where we have, this is our real function, u of xy, and this is our imaginary component function, v of xy. Okay? So let's compute the partials. Partial u partial x is equal to what? E to the x times cosine y, right? E to the x times y. Anything involving a y is a constant when we take the partial derivative. I think we remember
Well,
that.
that's also the plus I e to the x sine y.
Right, so I'm just taking the partial of u.
Yeah.
No, you're fine. That's good. Okay, so there's my first partial derivative of u, and again, just out of convenience, I'll write the partial of v with respect to y here. Just, I write it in this unconventional way just because I'm using the Cauchy-Riemann equations, right? So it'll be easier for me to compare. So the partial of v with respect to y is what? Okay, so we have e to the x is just treated like a constant, it only involves x. What's the derivative of sine of y with respect to y? Cosine y, yeah. So we get e to the x, cosine y. Okay, so that is to say, one of our Cauchy-Riemann equations hold. Okay, let's check the other one. So I'll differentiate u with respect to y. Again, e to the x is a constant with respect to y. What's the derivative of cosine y with respect to y?
Negative sine.
Negative sine. Good. Negative e to the x sine y. And the partial derivative of v with respect to x is what?
E to the x sine y.
E to the x sine y. Okay, so in other words, our second Cauchy-Riemann equation holds, right? Because these differ by a sign. One's negative, one's positive. Okay? So the CR equations hold for all v equals x plus iy. Okay? And all our partial derivatives are continuous, right? All these functions are continuous. They're all elementary functions of a real variable. Multiplied together are still elementary functions. And first, partials are continuous. So this implies f of z equal to e to the z is entire. Okay, good.
If you were being more like step by step, you would say the f of z is differentiable everywhere. And then since it's differentiable everywhere, that means it's an open set. So it's entire.
Yeah, well, yeah, I'm assuming that based on our discussion, right, the complex plane altogether is open in the complex plane, right? If you take any set with a topology on it, that must be an open set, both open and closed, as we discussed when we discussed topology. Yeah, but again, if you wrote this, I assume that you understand that. I don't think you could make this leap without knowing that those definitions hold. Maybe that's me giving you too much credit, but I believe in you. I believe in you all. So I wouldn't require you to write that. But you're right, if I was like writing a computer code, yeah, I would say that. Or many more steps than that, but yeah. Yeah, good. Okay. So, I mean, I should also say, I shouldn't have erased this yet. I should say, unsurprisingly, f prime of z is just equal to du, for example, du dx plus I dv dx, right? I'm just choosing the fact that I'm approaching horizontally, Remember, it doesn't matter. If I'm differentiable, it doesn't matter which direction I choose. So I'm just choosing this particular path of approaching. Okay, so let's just plug this in directly. What do I get? I get e to the x cosine y plus I times e to the x sine y. That is, the old familiar identity holds. The derivative of e to the z is equal to e to the z. I could have equally well chosen the derivative, the partial of v with respect to y for my real component, and the negative of, the negative of the partial of u with respect to y for my imaginary component. I get the same thing. You can verify that for yourself right here. Right? Okay. Okay, good. How are we doing on time? Oh, great. We have plenty of time. So here's the theorem. Let's assume that F is analytic in domain D, and here I mean topological domain, open and connected. Okay? And F prime of Z is equal to 0 everywhere in D. Okay? Then F of Z is constant in D. Okay? This is the type of theorem that is just a sanity check, right? Where if we have some condition that's familiar to us, remember this from real variables, or we even made a little bit of a flimsy argument about a function of two real variables, or their first partials being 0 in an open set. If they're all 0, we get a constant function for our original function. And so this is telling us that somehow we have a good definition of analyticity because we recover this same type of result. Okay? So let me just write a couple lines that justify this. So f prime of z equal to 0 in D implies all first partials of u and v vanish, right? This is kind of just what I was saying here. The derivative of f is just expressed as the first partials, whichever way you like, of the component functions u and v. Okay, so that is to say, what do I mean by vanish? I just mean that they equal 0, right? That is to say, du dx is equal to du dy is equal to dv dx is equal to dv dy is equal to 0. By what we proved before, this tells us that both u and v are constant because we're in a domain, an open and connected set for our domain of definition. Okay, so that is to say, u comma v are constant functions which in turn implies that f of z is equal to u plus iv is just a constant in the complex numbers, right? Okay. Good. I'm glad that we've had some really thoughtful questions about what analyticity actually means and how it's different from differentiability and how to compare that with the difference between real functions and complex functions. Now, I want to take a slight physical detour. We're going to, again, very briefly, talk about a certain differential equation. And it turns out that this differential equation has furnished to it many solutions just by the definition of analyticity. Okay? That is to say, analytic functions give rise to solutions to a certain differential equation of second order. Okay? We characterized analyticity in terms of a pair of first order differential equations, the Cauchy-Riemann equations. It turns out the story gets even better. Analytic functions, that is to say complex analytic functions, usually the distinction goes the other way. If you want to specify a real analytic function, you say real analytic. When you say analytic, usually it's implied that you mean complex. That's just a weird cultural thing. But we'll talk a little more about that later. What I mean to say is that the second order partial derivatives of the components of analytic functions, the real and imaginary parts of analytic functions, satisfy an equation that comes up in physics a lot. Okay, so let's talk about harmonic functions. Okay, so anybody who studies physics has probably encountered this, at least in passing before. The Laplace equation, Laplace, is the second order differential equation. Okay, so here's some physics notation. The gradient squared of phi, some function of xy, is defined as, okay, I don't expect you to know what this means. In fact, it's just a piece of notation. What this is defined as is the second partial of phi with respect to partial x squared. Take the partial derivative of phi with respect to x twice, plus the partial squared of phi partial y squared is equal to 0. This is the thing we care about. I only tell you this because it's common notation in physics. Okay.
I've actually never seen it in only two dimensions.
Yeah, so why are we only looking in 2 dimensions? Because we're dealing with complex numbers, right? But yeah, you can generalize this to a function of n variables, right? You just sum up the second order partial derivatives with respect to each variable and set that equal to 0. So, good, so we have some experience with this. And if you don't, that's okay. But the solutions to this are, they come up everywhere. Electrostatics, magnetostatics, fluid flow. There's an example in the textbook that says something about stretching a membrane across a loop of wire. I don't know how people came up with that or where that comes from really, but still, nonetheless, it's amazing that the solutions, the functions phi that satisfy this differential equation somehow give some physical description of all those different types of things. So people kind of go nuts for this type of thing. And magically, our work in complex analysis, our work relating to the theory of analytic functions, furnishes many, many solutions to this equation. Okay? So, let's characterize such functions. Functions. From a C perspective. A complex perspective. What can we say about the nature of the functions phi of two real variables in terms of complex analysis? Okay, so let me, it's on the next board for emphasis. So, definition. Let's assume phi of x comma y, real values. Is called harmonic. In a domain D, okay, again I mean domain in the topological sense here, open and connected. Firstly, if all its second order partial derivatives exist and are continuous. Okay? So again, a little bit more than saying that its first particles are continuous. We are again differentiable, and those derivatives, those second derivatives, are continuous. And if at each point in B, the function phi satisfies the Laplace equation. I'm sorry, I also glossed over this. I try to stay on top of whenever I introduce a symbol that people may not have seen before. This is a Greek letter phi, a lowercase, like F sound in Greek. Is that okay with everybody? seen this before? Okay, just check. Sorry if that seems pedantic, but you know, it's better to check. Okay. So, here's the theorem. So, probably, I'll just state this theorem, and then, well, we might have time to prove it. There's some time left here. So, if f of c is equal to u of xy plus I times v of xy, is analytic in domain D, that is to say an open connected set D. Then each of u of xy and v of xy is harmonic in D. No wonder solutions to this equation show up everywhere. They're just the real and imaginary components of harmonic functions. I'm sorry, of analytic functions. Any analytic function you write down, the real and imaginary components of it give you some solution to this differential equation. That is to say, any analytic function gives you two functions which solve this differential equation. No wonder they're everywhere, right? People didn't know that when they first started studying the Laplace equation. Kind of cool.
Is there any sort of generalization to 3 dimensions?
Is there any sort of generalization to 3 dimensions? So what do you mean by that? You mean
It's like for this like theorem we have right here.
so do you mean 3 input variables for u and v?
Is there some type of
So okay, this is, let me go on an algebraic tangent here, no pun intended. So there's a theorem that says the only algebraic structures that lie over the real numbers are complex numbers, quaternions, and octonions, which each have respective dimension 2, 4, and 8 over the real numbers. Okay, I'm saying a lot of things here that I haven't said precisely. Right? This is like way far afield from where we are. So the answer is no. There's no multiplicative structure for that mimics the complex numbers in any fashion, except in dimensions 4 and 8, beyond the complex numbers. Okay, that is to say, the complex numbers are a thing called a real algebra, an algebra over the real numbers. This is some ring which contains the real numbers in a nice way, such that they're the commutative things, scalars. Okay, and it so happens that the complex numbers are commutative as well, but the quaternions and octonions are not commutative, but they still qualify to be algebras which treat R in a nice way. The real numbers commute with them.
Is it specifically 4 and 8, or is it just not worth going to like 16?
No, it's specifically 4 and 8.
Okay.
Beyond that, it's not workable. Pretty bizarre, right?
Yeah.
Pretty bizarre, yeah. So if you're interested in that, look up the classification of central simple algebras over R. It's a decent Wikipedia page on it. I was reading it the other day. So yeah, no obvious generalization to this. Possibly something in 4 dimensions, but nothing I've ever seen. That's something to think about. But then you have to really study the structure of the quaternions, which have a different law of multiplication than complex numbers. Sorry.
IJK
Yeah, right. You have an ij and a k instead of just an I.
times J is K.
Yeah, but then you also have to talk about what
J.
I times j times k is, and make sure that those do those three things commute.
No.
No, right. So yeah, the multiplication becomes quite a bit more complicated.
Oh, okay.
It's not commutative.
Is it associative?
It is associative. The octonians are not associative. You lose more structure every time you go on.
Is that why you can't go to 16 and just lose everything?
Yeah, pretty much. Yeah. So do look at the page on the classification of central simple algebras over R. What's this? It's Brouwer's theorem, I think, or the Brouwer group. The algebras actually form a group under this thing called tensor product. Anyway, this is way off topic. Right. So. Okay. Let me give you an outline of the proof of this theorem really quick. Okay. Here's how nice analyticity is. First of all, I'm going to tell you a lemma, which we'll prove later. It'll be easy for us to prove it later, but we'll exploit it now. You know, take my word for it, or maybe prove it at home. So, f of z analytic implies that u and v have continuous partials of all orders. Okay, wow, that's pretty powerful, right? To say that I'm analytic, that is, once complex differentiable at each point in some open set, means that I have arbitrarily high partial derivatives for each of my component functions at each point in that open set where I'm analytic. Analyticity is really powerful. Okay, we're actually saying a lot more by saying that we're differentiable at each point in an open set in the complex plane. And this is a glimpse of that. Seems very innocuous when we write the condition down at first, right? It's like, oh, okay, we're not just looking at a point, we're looking at an open set. It means a lot more. Okay? All right. So, I promise we'll prove this later. If you don't believe me, you can read ahead. The proof is in chapter 3. Okay, I guess actually it's 3:15. I'm out of time. Let me just tell you, we'll appeal to Clairaut's theorem. I don't know if you remember that from Calculus 3. It just says that it doesn't matter the order that we differentiate in with respect to each partial, right? We'll appeal to Clairaut's theorem and the Cauchy-Riemann equations. And that, it basically follows straight from that. So we'll do that on Tuesday. And then we'll talk a little more about, hopefully, some stuff you remember from Calculus 3, level sets and gradient vectors. And then we'll end our detour into physics for a while at least. We'll go back to studying analyticity and multi-valued functions is what we'll talk about after that. Okay, so have a good weekend. And if there's any further questions about the problem set, just let me know over email. I'm going to try to stay awake later this evening, but no promises, I might fall asleep. Okay, so see you Tuesday.